Welcome back, everyone. And I'm pleased to announce the second session of the Living Through Touch Symposium, which will be focused on sensing. The work that's going to be presented here is going to be presented by myself. I'm Raymond Holt from the University of Leeds in the United Kingdom, but it does represent a collaboration across a number of partners in the project, and you'll hear a little bit more about their work as it goes on. But in particular, the work that we've done has involved Leeds working on sensors, but also our colleagues in Greece at SUITCEYES, who've been working on some of the visual analysis and computer algorithms behind it that we'll be presenting today. So I'm also joined by Panagiotis Petrantonakis, who's over in Greece. We'll be available to answer any questions that you might have at the end of the presentation. If you do have questions, feel free to use the Q&A button down at the bottom of the screen. You can type those in, we'll see them, and then we will work through them at the end of the presentation. I hope you enjoy it, and all that remains is for us to set the presentation playing. Thank you. Hello, I am Raymond Holt from the University of Leeds in the United Kingdom. I am here to present today on the sensing aspects of the Suitcase project. And in this presentation, I'm going to provide an introduction to the haptic, intelligent, personalized interfaces, or HIPIs, as we call them, that have been developed in the course of this project. I'm going to talk particularly about how we can use such systems to sense the environment and then communicate information to the user. The first part of the presentation will focus on this idea of haptic, intelligent, personalized interfaces, or HIPIs, and what we mean by that. And there's something you'll be encountering a bit more later on in the day as well. But the second part of the presentation will focus on a particular HIPI, a prototype that we have built to demonstrate the use of haptics for environmental awareness. Now, in order to talk through this, I'll talk a little bit about the actual physical design of the prototype. I'll then talk about the way that we do visual analysis and what that means. And also an important idea, which is that of semantic reasoning and how that can be used to help inform the sensor information, the information we take from the environment, and communicate to the user. And I'll give an example of how these can be used through a process called active object search. So the goal of the Suitcase project is to develop haptic, intelligent, personalized interfaces, and particularly with the aim of enabling and supporting people with deaf blindness. Now, the phrase haptic, intelligent, personalized interfaces is a lot of jargon and quite complex. So let me just go through each of these terms in turn to talk about what they actually mean in practice. So firstly, HIPI, haptic, intelligent, personalized interface, is an interface, as the name suggests. That is, it is a device that enables a human user to interact with their environment in some way. So in this particular case, by, for example, receiving messages from other people, identifying objects, people, and places that may be in the environment, and also orienting yourself. So working out where other objects, people, or places are in relation to yourself, and where you are in relation to the environment. So in this sense, it's an interface. It allows a person to interact with their environment through the device. It is also personalized. That is, it is adaptable to the varied needs of individual users.
And that's something that's very important. We know that people who are deafblind are individuals. They have different tastes, but they also have different degrees of vision or hearing. They have different experiences of deafblindness and dual sensory loss. They have different paths through that and different strategies that they've learned. There isn't what you might call a one-size-fits-all solution. A device is going to be great for every single person with deafblindness. So what we've aimed to do is to develop not a single system, but a platform for developing systems that can be adapted to individual needs. Now, this may mean that we can build different HIPPIs that do different functions. So some, as you will see later on today, are focused more on communication. Some might be focused more on navigation or gamification. They can be personalized in the sense of the sort of objects and places and people who can be recognized can be tailored to those of interest to a particular individual. Equally, we may use different sensors for different people or different users, so that you might have a version or a HIPPI that has very expensive sensors in it and a lot of computing power, or you may have one with much cheaper sensors in because you don't need all of that functionality. And therefore, you want something that is lower cost but can do the things that you do need. And finally, you may have different types of feedback. So we'll be hearing a little bit more about haptograms and haptic communication, that is communication through touch. And there are different types, and the sensitivity of different individuals varies. So the ability to customize the haptic feedback to an individual is very important. So this is something that we've tried to do. So this isn't just one interface device that everyone must use. It's an interface that can be customized to individuals. Then a HIPPI is intelligent. That is, it gathers information from the environment and it interprets it in some way. One of the things that you find is that what our brains interpret from our senses is not all of the information that goes in. Our brains are very good at focusing down on the most important information and ignoring the rest. And that's really important because otherwise we would be completely overwhelmed by irrelevant information. And the HIPPI, by using machine learning and artificial intelligence methods and computer vision methods, which we'll talk about a little later in the presentation, tries to apply the same principle, that rather than just bombarding the user with information, we try to select information that the user will be interested in. For example, you may attempt to detect particular landmarks in the environment. So where am I? Am I in an office at the moment? Have I just passed the entrance to a building? But also importantly, one of the aims is that the HIPPI should respond to user queries about the environment. That is, information should be pulled by the user and requested by the user rather than just thrown at them. So rather than just trying to guess what the user wants, we try to allow the user to send some queries. So we'll talk a bit more about that in the course of the presentation. Finally, a HIPPI is, of course, haptic. That is, it needs to communicate information through the sense of touch. And that's something we'll be hearing a lot more about later in the day, about human perception and social haptic communication in other presentations. So I won't talk too much about it here. There are lots of different modes of haptic communication that can be used. We have opted for vibration. In this particular case, using vibration motors. Other methods can be used, so pressure, temperature, and so forth. But this presents some really serious challenges because actually converting information from one set of sensors into a series of vibrations that can be understood by people presents some real challenges. Other presentations today will be addressing that aspect. So, say a hippie is a haptic intelligent personalized interface. It is something that is adaptable, that can take information from the environment and communicate that information at the user's request through the medium of touch. It's important to emphasize that these can come in different forms, and actually you're going to meet several different forms of hippie today, because we've developed several for different purposes in the course of the Suitcase project. So yes, they can be wearables, for example. So you'll meet a vest in this presentation. There's also a gaming vest that we will be presenting, which focus on taking information from the environment and allowing the user to respond to it. But also there will be wearables for communication, and also furniture. So we have something that we call the chairable, which is something that can be attached to a chair, demonstrates that actually we're not just thinking here about completely portable wearable devices that create particular constraints on people, but that also the sort of platform that we're developing can be used to make more static devices that may be useful in communication situations. And you hear a little bit about the sort of person-to-person communication, or the opportunities perhaps to communicate from one person to a number of different people using these hippies and social haptic communication. And of course, our aim as the Suitcase project comes to a close is that future projects will begin to address these issues. So this is what we mean when we use the phrase hippie, haptic intelligent personalized interface. But to try and demonstrate the work that we've been doing, I wanted to talk about a particular prototype, one of the hippies that we have developed, which is a system intended for environmental awareness. That is a way of gathering information from the environment and informing the user about things that they're interested in the environment. So the goal for this prototype was to help the user in navigating their environment. So to an extent, this is about avoiding collisions, warning if you're about to walk into something, helping you to identify where you are in relation to important features, but also to help the user identify objects and people of interest in the environment. So that covers both person recognition, by recognizing people's faces, recognizing particular objects, and recognizing scenes, that is, what environment am I in at the moment. And an important note is that clearly, as you're walking around and perhaps gathering information through a camera, there are huge amounts of objects that could be recognized, and you don't know which ones are of particular interest. So just constantly sending signals to the user, trying to narrate everything in the environment is going to be overwhelming for them and very difficult for the system to do and extremely slow. So really what we want is for the user to control the flow of information by sending queries. Now this might be done using a mobile phone application and using particular symbols to request a particular query. It may be done by using little tap sensors that we've got, where a user can tap in particular ways in order to activate particular functions. It may be done through a computer, depending on the particular context of use. But the idea is that we want the user to send out a query, and then the hippie will do its best to answer that query. And I'll talk through what all this means in the coming slides. So the image that you see here is principally towards the left. You see an image of the prototype hippie itself. It is a black vest, and we see on the left and right shoulders there are two ultrasonic distance sensors, two little round shapes that are poking out of it, pointing up at shoulder height. And again, so a similar set of three down at the waist of the vest, pointing one forwards, one to the left, and one to the right. These are ultrasonic distance sensors. They will detect when you are at risk of colliding with an obstacle. So they're there to provide a warning. And this is the sort of approach that is used both in parking sensors for cars, but also in technologies such as the ultracane, which is a cane that combines ultrasonic distance sensors and some warnings in the event that you're about to collide with something. At the center of the vest, we see a small sort of silver and black object with a number of little cameras inside. And this is a depth camera. So that captures both images, as a normal camera does, but it also measures distances, objects that are directly in front of it. And this information is given over for visual analysis. It helps the system to recognize not just what something looks like, but also its three-dimensional shape as well. And the whole thing is operated by a mini computer that is worn on the front in a little pocket. So actually you can't see the mini computer itself. It's contained inside the black pocket and hidden away. And below that is a battery that provides a power supply. Finally, towards the top right, you can see that it communicates using Bluetooth, which is a form of radio signal, to measure the proximity or the distance to beacons, eye beacons that are placed in the environment. You can see at the top right here, there is a little picture of an eye beacon. It's about 4 centimeters long. And the idea is that by measuring the strength of the radio signal for that beacon, the hippie can determine how close it is, approximately. It's not very precise, but it can tell, something within a meter or so. Is it, more like 3, 4, 5 meters? Is it 10 meters away? So it can do a bit of kind of proximity detection, and also whether you are getting closer, that is, the signal getting stronger over time or weaker as well. And the benefit of these is that whereas the other sensors on the hippie require things to be in their line of sight, so the ultrasonic sensors can only pick up things that are within their sort of cone of view. The depth camera can only pick up items that are again in its field of vision. The eye beacons don't need to be seen by the system. So if they are behind you, or if you happen to walk past one, you can still pick up information from them. And in this way, they can be used to label things of interest in the environment. So you could, for example, have a person wearing a badge that contained one of these. And that person might be moving around, but you would know roughly when they were close to you or when they were further away. Or they might be used to mark objects of interest. You might use one on your mobile phone or your laptop, or they might be used to mark out landmarks in the environment, the doorway, the lift, the staircase, and so on and so forth. But the idea is that between these sensors, we can use different analysis techniques to help inform the user about important features in their environment. On this picture, I've tried to show a little bit about how the haptic feedback is delivered. I'm not going to say a lot about it, but I thought it is important to give you some indication before other presentations talk on it in more depth. It is a complicated diagram. What you see, basically the vest as if it had been opened out. On the left-hand side, you see the front of the vest with the camera in the middle and the ultrasonic distance sensors. On the right, you see the back of the vest. And the things of interest, although there are many wires shown on here, it's the ones in orange that are of interest to it. So we see there are vibration motors, one on each of the shoulders. There is then a 4x4 grid of 16 vibration motors on the back, which are used to deliver more complex signals. And then around the waist, there are 5 vibration motors, one at the front, one at the sort of front left and front right, and others towards sort of back left and back right. And these are used to deliver directional information to the user. So just to give you a feel for some of the ways in which haptic feedback is being delivered. Before we look into detail at how we use some of the information from the sensors, this slide gives a diagrammatic representation of the flow of information through the HIPPY. Over on the left-hand side, you can see we have the garment itself. And the garment, using the camera and the iBeacon signal strengths, will pick up on these as environmental cues, which are then sent to the visual analysis, in the case of camera data, or sent as proximity data. And these are passed on to the semantic knowledge base, which is basically where all the information that the system knows is held. And the semantic knowledge base will then apply some given rules to try and make inferences about this information that has come in. And based on this, they will then try to send feedback to the users. So this will take the form of a message, which might say that a particular person has been identified, or you are in this particular room, or something of interest is nearby, and it will then send that as to the haptic signal generator in the vest, which will then convert it into haptic feedback, an appropriate signal to be sent to the vibration notice. Now, it's important that this is driven by the user's needs and not just sprayed continuously with information. Therefore, we also have the fact that the feedback is controlled not just by what the knowledge base is picking up from the sensors, but also by the queries that the user has given. It's those queries which determine what the knowledge base is going to work out about the environment from the sensor data. And in this way, we try to give only relevant information to the user and allow the user to control the flow of information. Now, there may be some case in which we wish to override that, perhaps an alert, for example, if you're about to collide with something, or if something significant appears to be happening in the environment. But in most cases, we want it to be the user who is driving the information. Now, we've talked about the sensors that we're using, and they gather a lot of information from the environment, both in terms of what beacons are present, but also what is being seen by the camera. So a real challenge is taking those images and making sense of them through a computer, and that is what the visual analysis component of the system does. Visual analysis, or computer vision, is a way of detecting objects and people in the environment using artificial intelligence algorithms. And there's actually a huge number of these that can be identified. So on the right-hand side, you see an example. Here is an image that has been analyzed, and we can see that the recognized items have rectangles drawn around them and have been labeled. So we see towards the right-hand side, a mug has been recognized. Towards the front of the image, a book has been recognized. And just behind the book, over towards the top left of the image, we see a cell phone. And these have all been labeled by the algorithm. And you can train the algorithm to recognize different things. So in some cases, it may be a question of recognizing a book in general, or it may be a case of recognizing a particular book. We can do face recognition, so you can recognize both when a person is there, and you can recognize when a particular person is there. So it may be the case, okay, there's an unknown person here. The system knows it's a person, but they don't know who it is. Or it may be the case that actually here is your friend or your brother or your sister, somebody who is known. And the idea is that you can actually adjust the list of objects and people of interest to suit a particular user's needs. So it's not the case that everybody needs to recognize everybody else in the world. For any given user, there will be specific things that they're interested in, and we can train the algorithms towards those particular things. Another recent development is that in the course of doing face recognition, we've also, in light of the COVID-19 pandemic, been looking at developing the system so that it can now recognize a person wearing a face mask. So you can tell if somebody approaches you, is it a person who is wearing a face mask or is it somebody who is unmasked? Which is something that we know is of concern to some of the people who we have worked with on this project. An extension of this is that actually, as well as recognizing individual items, the system can also recognize scenes. That is, it can work out what sort of environments you are in. So we see on the right-hand side an example of this. Once again, we have the image, we have some recognized items that have been highlighted. So a laptop at the front, in the middle of the image, we see it's a computer, a desktop computer in this case. Over to the right, a person, an unknown person, being identified by their face. But the system as a whole has recognized this as an office environment. And as with objects, the list of places that can be identified can be customized to particular needs. So you might be looking at recognizing living room, an office, conference room, a corridor, an elevator, staircase, and so forth. Or maybe a case of recognizing my living room, opposed to just a living room in general. And of course, this is also useful for navigation because it helps the system to know what rooms it may have passed through. So if you know that you've gone down a corridor and passed a set of stairs, then this may be useful in helping the user to navigate or orient themselves in the environment. Now, the problem with all this information is that we're recognizing things all the time, and I've already mentioned the fact that we need to do something to reduce the amount of information that is being sent to the user. That is, there's lots of stuff that the user isn't interested in, and a small amount of stuff that the user is interested in. But the challenge is in how we make sure we're giving the user the stuff that is of interest and not withholding important information, but at the same time not overburdening the user with very complex instructions. That is where something called semantic representation and reasoning comes in. This is a way of processing information and beginning to make sense of it so that we can pick out the stuff that is most important to the user. So the idea is that you go from a high-level concept and come into a phrase that makes more meaning. So we have concepts that are detected by the visual analysis tool, and then we turn those into language that can inform the user and convert it into a haptic signal. So we have a little flowchart here that shows the process. On the left, we see that there is a prototype vest with the cameras and other sensors, such as the eye beacons. This sends its information to the visual analysis tools, which then detects objects of interest, people of interest in the environment, scenes of interest, and so forth. Then the semantic reasoning system in what's called the knowledge base translates these into phrases. So if you're interested in trying to find out where the table is, it might come back and say, the table is on your left side, far from you, in your field of view. Or it may say, the table is on your left side, carry straight on, depending on the context of the question. And it is important that the user is able to deliver queries to the system. And because otherwise we do run the risk of just spraying them with information. So part of the idea is to have a set of predefined queries that you could use. And again, these queries can be customized to different people, and they can be combined from some sort of basic question types and then some objects of interest. So the user might, as an example, say, where is my phone now? So basically using the where is instruction and the phone instruction. And the system would gather the visual information, look for the phone in the images and say, your phone is located on your left and it's close to you. perhaps using the proximity sensors, the iBeacons, and or the depth information from the depth camera. Or you might say, where am I now? In which room am I currently located? And the system would use the scene recognition and then say, you're located in the conference room, or whichever room it happens to recognize. Now also, the knowledge base can remember where things of interest have been and which rooms they were in. So you might say, where and when was my cell phone last detected? And the system could look through its records and respond, your cell phone was last found in the living room 10 minutes ago. So that may be where you want to go in order to look for it. And there are other questions along these lines. So things like, what objects are on my left? How many people have been detected close to me? Is there anybody I know in the vision? Is this person close to me wearing a face mask at the moment? So the idea is you would have a series of defined queries that the users could begin to put together in order to interrogate the sensors for information that was of use to them. So just to give an example, we've developed an approach called active object search, which is trying to use the sensors in order to help a user to identify where an object of interest is within an environment. And the idea is that this guides the user towards a predefined object of interest. That might be your cell phone, it might be your laptop, it might be a book, it may be a particular person, for example. And the idea is it uses a combination of visual analysis, recognize objects, and proximity information from the iBeacons to identify how close a target is if it is not in view. And this approach is triggered by a query from the user who will basically say, where is what I'm interested in? Or actually to find my water bottle, find my cell phone, etc. And the hippie will then go through several search modes, or several modes. The first is search mode, then guided mode, and finally a final approach mode as you get gradually closer to the object. I'll just talk you through these for a moment. So here's some examples. So in this case, when the user makes the query, find my object, the first thing we do is check, is it in camera view? It might be right in front of you. If it's not in camera view, then the hippie sends a signal to the user using the shoulder vibration motors to say, it's not in view, we need to be in search mode. So at this point, the user begins to move around and explores the room until the object is detected by the camera. So we want to try and move around until it comes into view. Now, for this, we use the proximity information from the iBeacon, if the object has an iBeacon on it, to inform the user if they're getting closer or further away. And in this way, they can get close to the object and then basically rotate until they get it in their view. And we have some examples, photographs here of this in action. So we can see the user enters the room. So they may have placed a query saying, where is my water bottle? The water bottle was last seen in the office 20 minutes ago. They enter the room. We recognize that it is an office. It has computers and tables in it. But the water bottle itself is not seen. So the user must now explore the area, but can get some information about whether they're getting closer or further away from the target. In this case, is a water bottle. Once the target object is detected by the camera, the hippie then sends another haptic signal, notifying the user that it's now going to go into guided mode. And at this point, it can see the object, so the aim is to keep the object in view and try and use the vibration motors on the waist to convey the relative direction and distance from the target. So here, you know where it is in the camera view. If it's over to the left, you need to turn towards the left. If it's over to the right, you need to turn to the right. If it's straight ahead, you need to go straight forward. And it can tell you when you're getting closer to it. And again, we can see, in this case, the water bottle is actually on top of a chest of drawers, right over at the left-hand side of the image. So in this case, the user has now picked it up and has begun to steer towards that chest of drawers and the associated water bottle. Once the user is close to the target, certainly within a meter or so, the user has another haptic notice to say this is final approach mode, which is really that at this point the user should be able to reach out and grasp the item in front of them. The only haptic sensation is really to tell them where it is in the camera view. So if they start drifting off to the right, it'll tell them to turn left. If they start to drift off to the left, it'll tell them to turn right. At this point, they should be able to explore the environment and find the object of interest with their hands. Now, obviously, there are lots of other things that can potentially be done with these sensors that we have. So navigating an environment, working your way around an unfamiliar area and getting information about where you might need to go next, for example. But this is just one simple example that we've got to try and illustrate how we're using these hippies to capture information from the environment and then send it to the user in a way that is useful to them. So that brings me to the end of my presentation. I have introduced the idea of haptic intelligent personalized interfaces as being not an item, but a set of items or a platform for developing items that we have been producing over the course of the SUITCEYES project. And you will see several others over the course of today, but they all share the same features, which is that they try to act as an interface between the user and their environment by gathering information from the environment and informing the user about it haptically, but importantly, they are personalized. That can be adapted towards particular users' needs and not just having one size fits all. And we've given an example of the hippie of a system for environmental awareness that can use visual analysis and semantic reasoning to take information from a camera, so information that it finds visually, information from eye beacons in the environment, so by indicating how close it is to them. And we've got an example of using that to actively search out an object. That was everything that I wanted to talk about today.
All that remains is to say thank you very much for your attention. The work that has been presented here has been a collaboration between several partners on the project, particularly between ourselves at Leeds, who have been developing the sensing elements, and our colleagues over at the Centre for Research and Technology Hellas, or CERT, over in Greece, who have been developing the visual analysis and semantic reasoning components. So if you have any questions, do feel free to send an email either to myself, Raymond Holt, or to Panos Petrantonakis over at CERT. I've included our emails here, r.j.holt@leeds.ac.uk, or for Panos, ppetrant@iti.gr. Thank you very much once again for your time. Okay, thank you very much for listening to the presentation. I can see that a number of questions have appeared in the question and answer section. Some have also appeared in the chat. So I'm just going to try and work through those in turn. We've only allowed about 5 minutes for the questions to be answered, but I'll do what I can in the time that we have. And then at 1:45, perhaps those who wish to go for a break can do so, and I'll try and work my way through the remaining questions, and other colleagues may wish to contribute as they feel they are needed. So the first question that we have asks, why has vibration been chosen for haptic feedback rather than pressure? And this is a good question, because when we look at things like social haptic communication, it is delivered by applying pressure typically to someone's back or other parts of the body, rather than by vibrating them. So when we say haptic feedback in a mobile phone, for example, we think of vibration, but lots of forms of communication, like social haptic communication, are not based on vibration. We have explored the use of servo motors, which are motors that will basically apply a certain amount of pressure. We've looked at solenoids that will kind of use a tapping effect. And we've also looked at linear actuators. These are very large compared to vibration motors. Vibration motors are very small, sort of the size of a coin, whereas solenoids may be several centimeters in length, particularly if you want one that will give you enough power, and that makes it very bulky to incorporate into a wearable. So for a static device, and if we look at devices such as Hapticon, for example, that uses solenoids, but that is something where the device sits on the desk and you would put your hand on it and it will tap on the fingers to reproduce finger spelling. In our case, because it's a wearable, we aren't able to do that. So in the end, we settled on vibration motors as being small and portable and relatively cheap for the device. So that's the reason for using vibration. We've also had a couple of really good questions about the sort of applicability of the clothing. So one of those is the observation that the vest shown is very clearly designed for a man. And how does that affect the fit if, say, women want to wear it? Not just in terms of the comfort, but in terms of how well the sensors work, because your depth camera that we're relying strongly on is going to be pointing at different angles. And this is a really good point, I think, and one that's really significant for the project. And I think we will hear a little bit more about it in the wearables presentation later on. And that is, it's very difficult to make a garment that is literally one size fits all, particularly if we wanted to make it into something that's perhaps a bit more discreet, rather than looking like something with lots of buckles on. So the thing to be aware of is that what I've shown here is a prototype for doing lab testing of the ability to interpret haptic signals to navigate an area. So this particular hippie you've seen is designed for doing experiments. There are others that you will see, and to me the idea is that a hippie is more likely to be something that is personalized. And the one that you see there is designed for a medium-sized male, can be adjusted to some extent with straps. The depth camera is actually on a rotatable mount, because you find that even the height of the user makes a difference to the sort of angle that you want the camera to be at. So that is personalized or personalizable in that sense. But I think if we were looking at developing something as a product to be used by a user out in the world rather than in a lab, we would then need to look at more directly customizing it to their particular needs. It's also worth noting that for some users, they may not want all of the sensors. They may not want to have the ultrasonic sensors on because they're not that worried about collision avoidance. They already have very good strategies dealing with that. So if you only want the visual components, you only need the one camera. So again, there's no reason why it needs to be a whole vest garment. It could be something that was much smaller to fit under clothing. It may be the case that you need to have a design whereby the camera could be fitted over clothing and attached using Velcro, for example. So there are lots of different options that are possible. So I think we have to be careful not to present this as being the hippie. This is one example of a hippie. And I think there were some good questions related to that about, well, actually, you know, my patients don't want to have a device that makes them stand out. You know, they don't want to be kind of singled out as needing assistive technology, perhaps, or at least they would like to have more control over what it looks like and what it communicates about them. So I think, again, this is something that we're trying to address through the personalization aspect. I'm conscious that we have now come to 12:45 and there are still 2 questions that I haven't answered yet. So I will quickly look to Nazreen for suggestions. Is it worth me carrying on, or shall we let people go for a break? And
I think we should keep the break and you can answer them in writing. And if people are not happy with the answers or would like to discuss more, we will have the mingle after the sessions, and please feel welcome to come there.
okay. I'm conscious, I think that the Q&As are only seen by the panelists. I don't think the answers are actually seen by everybody. I'm not sure. So obviously I'm down as a panelist, so that's what I see. So I will put the answers in the chat if that's okay. Okay, well, thank you very much. As I say, I will answer the remaining questions in the chat, but otherwise we will call this session to a halt and let you have a 15-minute break before the next session, which will be on perception, begins at 2 o'clock CET. Okay, thank you very much for your attention.